Okay, so now, today I would like to expand to high order systems. Systems that are in this form, we want to understand the response characteristics. So that's the general target that we're shooting today. System that has n poles and m zeros. And these poles and zeros, they can be real or they can be complex. So this is a general representation. And what we know now so far, think about it, we know now these first order system, we know now. We also know second order system. And there is just a few things that we need to go from here to here. First is we have definitely more poles. So we need to think about how, when these poles combine together, how the response will look like. Second is this. What we have talked about is the numerator is relatively simple. You can see the numerators are doesn't have zeros. All the two cases that we talked about doesn't have zeros. For general system, the zeros will also play some role over there. So what we're going to do now is first go through the step of just combining the poles, make the zeros to be simple, and then we generalize from there. So that's the general thought process. So let's start with just these two combined together. Let's say GS is S plus alpha S squared 2 zeta omega n S omega n squared. All right? So just the new denominators, numerator is simple. This one based on the same logic. So let's talk about step response. That means my input is 1 over S as unit step, and then the output is going to be y over g of S times 1 of S. So it equals and we can do partial fraction expansion to decompose it into 3 terms. So I will just write the structure SK1 and then second order term sine cosine functions here, and then a exponential decay function. So the structure in the time response will look like this. Y of t will look like, because of this and going through inverse Laplace transform, we're going to have k1, 1 of t, and then I'm going to use e negative zeta omega nt, sinusoidal components inside, I'm going to use k5, so first order goes to e negative alpha t. Coefficients doesn't change. K4 is the same as K4 here. And in the middle, we have sinusoidal components. And I used K5 and K6 to indicate that they may not necessarily be the same as these K2 and K3, because we have to decompose this into sine and cosine Laplace transforms. But the structure is like this. So if we plot the locations of these roots of the poles, it's going to look like this. We have one root at the 0, and then one root real, somewhere here, let's say negative alpha, and then a pair of complex conjugate roots. And depending on the numbers, they can be at different places. So they can, let's say, somewhere here. So what I would like to do next is to, suppose you're given this, and then you know a pole 0 map like this, or more specifically, just a map of the poles. I would like to develop this intuition of how the response will look like. Okay? So first of all, if this complex pole, if it's closer to the imaginary axis, how would the response be? Would it be more oscillation or less oscillation? If this is moving in this direction, more oscillation, right? So it's closer to this marginary stability bound. So more oscillation this way. And then if this pole moves more towards the left, would this component be decaying faster or slower? Faster, right? So let's now just consider some boundary extreme cases. So if extreme case, if these imaginary, let's give the numbers, complex poles close to J axis, the imaginary axis. This is real, this is imaginary. I will call this J axis. And then alpha is very much to the left. Alpha is pretty big. So alpha being a lot larger than 1 means negative alpha is going to the right, to the left of the complex plane. So that means this decays so fast, this moves so fast, and very quickly this is going to become small. Okay? So in the extreme case, this goes away, and we are exactly the same as what we derived last time. This is the formula for if we have just second order systems. Right? So then in this case, we are going to have similar to second order system response, approximately. So that's the observation. And what that means is that if in your transfer function, this one, the number alpha is very, very large, okay, then the effect of it will not show up very much in the time response. Okay, that's just the general intuition. But in practice, be careful. So this is just the trend. Now, in practice, be careful about the final value. So, the final value of the response, again, using y infinity equal to the final value theorem, is s at 0, s times y of s. That equals to, so some calculation over here, it equals to k omega n over s is 0. This s cancels with this s, so it's alpha times 0 plus omega n squared. So alpha times omega n squared, it equals k over alpha omega n. So that's the point you need to be careful about. Although the intuition will apply, the effect, the transient response of this one is very fast. But alpha influences the final value. So that means if you want to plot the system response roughly, you should target at something like this. The final value is k over alpha omega n. And then there will be oscillation. It's similar to a second order system. Value, let's see, initial value, let me check quickly. It's s going to infinity. Yeah, the initial value is still 0. So try to draw, it would be something like this. Okay, so initially slightly different from the pure second order oscillation, but eventually, very quickly, it looks very much like a second order response. So that's this extreme case when alpha is very, very large. So from there, the general rule of thumb, so let's talk about this condition. So what does it mean for being very, very large? So general rule of thumb is this. Okay, so rule of thumb, if alpha is 5 times further to the left of this, the complex conjugate pair, so the 5 times larger than the real part, which is negative zeta omega n. Okay, so maybe do it this way. So if this location, negative alpha, is 5 times to the left of this negative omega n, this real part of the complex root, then the effect can be considered, the transient happens very fast. The system response is roughly a second-order system. Then I love t is approximately a second-order system response. So in practice, that means you can very easily analyze this and check the locations of the poles and know the system response. If alpha is not that far away, alpha is relatively closer, then the response will be this superposition of different modes together. And in this case, we call these poles that are closer to the imaginary axis, these are the dominant poles of the system. Okay? So that's the first scenario. We have talked about the concept of dominant poles. If there are more of these, if there are many, many more poles, like these, real part, like this, then similarly, you just have more superposition of, if it's a real pole, superposition of these modes. And if they are very far away from the imaginary axis, they can all be discarded in the steady state response. So that's the first concept. And then you can apply this analysis to the case where you have complex poles that are very far away from the dominant ones. What's going to change? So if you have complex, if it's like this, and then there can be actually more second-order terms. The result is very similar. Your response is going to be step response. It's going to be more superposition of these terms together. So E negative zeta 1 omega 1 t, use eta, and then plus all right, so there will be more complex oscillations in these individual modes, but there will always be this exponential decay components. And if zeta 2, omega 2 is something like this, very, very far away from the first dominant pole, then you can see this part will decay very quickly. All right, so the dominant pole concept still applies. And then the rule of thumb also applies. If negative zeta 2 omega 2, this is the real part of the complex poles here. If this is 5 times further away to the left of the first dominant pole, then you can also regard the first dominant pole to be to define, to govern the response, especially at the steady state value. So I will, you can finish the writing of this part. I'll just verbally explain. The concept is exactly the same. Any questions so far? So that wraps up the analysis if you have many, many more poles, high order systems. The next thing is the effect of zeros.